Okay.
Hi, everyone. Please allow me to introduce the speaker today. The speaker today is Professor Luc Jaulin. Luc Jaulin was born in Nevers, France in March 15, 1967. He received the PhD degree in the automatic control from the University of Auxerre, France in 1993 and got the HDR degree in 2000. Since 2004, he's full professor of robotics at the École nationale supérieure de technique avancée, Bretagne. It's a very good engineering school in Brest, France. He does his research on underwater robotics using interval methods and constraint propagation in the robotics for exploration team. He's co-author of more than 250 papers in international journals and congresses. He received the Moore Prize in 2012 for his work on localization and map building of underwater robots using interval constraint propagation. And the title of Professor Jaulin's presentation today is a boundary approach for set inversion. Okay, please begin your speaking.
Thank you very much for introduction. So I will speak about set inversion, a boundary approach, and try to provide some new results on this topic, mainly to be more efficient. So if you have some question or if the sound is not okay, just tell me, not by chat because I will not, but via Andreas. Okay, thank you. So what is the main motivation of this talk? I will first introduce how a set inversion algorithm works when we use contraction method or contractors. First, we have an inside and an outside. So outside is blue, inside is magenta. And we have a box, and we have a boundary. And today I will speak about how we can be more efficient. And the observation is the following. A classical algorithm starts with a box, green, and performs some contraction. So the contraction from inside and the contraction from outside. The contraction from inside and outside are done separately. I mean, the computation to contract the inside or to contract the outside are almost the same. And they are done twice. And it is what we want to avoid here, because we don't like, just to be efficient, to do twice the same computation. And it is what is done classically. I want to avoid this. So we have a contraction and then a bisection here. And after, we generate two boxes with contraction from inside and from outside, and then bisection and contraction and so on. So it is, we produce a tree with boxes, and usually we memorize magenta and blue boxes and also yellow boxes, and we want to do better than this. So the idea is the following. When we compute just the boundary, like this one, instead of the inside and the outside, as we do usually, we produce exactly the same boxes, but we do not have the information concerning if it is inside or outside. So we can feel that it should be possible to take backward the information from the function, just in order to be sure that you are inside or outside. It is the idea. So to get the image on the right, it takes something like twice less computation than the one on the left, and we think it's not normal. So it is a motivation. Okay, so we want to avoid to do it twice, and what is important is to keep the information backward if you are inside or outside. Okay, so I have two images, and just to give the idea of what we want to do. On the left, we have boxes with classical algorithm, yellow, magenta, and blue. And here on the right, we have only 4 boxes, the yellow boxes, but we have some colors on the boundary. So we have just the faces of the box that have a color, which means inside or outside. So on the right, it is what we want to compute. Okay. So the idea, what we want to do is to use intervals, but the bounds of the intervals have some colors. So here, blue outside, inside, or unknown for yellow. So here it's orange, but it should be yellow if you want to be consistent with the previous picture. Okay. So I will recall what is a forward-backward sequence, because it will be important here. For a forward and backward sequence, usually, when we want to inverse a problem, we have a function f, which is given by a complex algorithm. And this function f can be decomposed like this one into many, so f1, fn, a simple function, so more simple function. And this sequence will be important, and it is quite classical in state estimation problem to deal with such set inversion problem with a composition and an inversion. So it is an inverse problem with a sequence of operation. And what we want to compute is a set of all initial states, such as the inverse by this complex function of y, and to intersect with an a priori set. This is what we want to compute. Okay. So what we do usually is we perform a forward-backward sequence. So
look, may I have a question?
Yes.
What does it mean, the inverse by f1 of y on the previous slide?
This one.
Yes, but the entire function f maps x into y, and f1 is just one of intermediate quantities, yes? Sorry, this is not
I have some problem to
I apologize.
Yes.
This is entire function f, sorry.
Okay.
No question.
Okay, so it's okay.
It's okay, okay.
Okay, so I continue. Okay. So okay. So the classical approach, and this one is not new. It's not related to interval analysis of set membership method. It also exactly the same reasoning when we use a Kalman smoother, for instance. We can use also for sets. It's always a forward-backward sequence. So probably I can try to explain here. Usually we have something like this: x dot. Oh no, excuse me. X k plus 1. Oops, sorry. Whoop. So we have something like x. I'm sorry. Okay, x. Okay, it does not work. I will come back here. I'm sorry for this. Okay. So I have a sequence, and I perform a forward composition of the function, and I will start with the initial box x0, and I compute the sequence, and k here corresponds to what we will call here the time. But in the initial problem, there is no time, but k here is seen as a time. Okay. And once we have computed this sequence, we perform the intersection with the last set, which corresponds to y, but here it is called like this, y. So we perform this intersection, and we get the backward set, which is here represented by the left arrow on the top. And then we perform a backward propagation from y up to x0. Okay. And we return this set. So it is what we call a forward-backward sequence. And here we can see this set x of k as a set of all states that are consistent with the past. And here the backward sequence is represent at time k the set of all states that are consistent with both the past and also the future. So it is this way we see forward-backward sequence in control. Okay. And if we want to implement this algorithm, it's difficult to compute with sets. And usually we need to deal with some kind of approximation. And in interval analysis, we use boxes. But when people try to formalize this problem, they use different type of approach. So you have the interval approach, but also you have the set membership approach. And one which is quite known, at least in France, but not only in France, is the approach by Couzeau. So I wanted to present this one because it's not so classical in the interval community, and it's not so complicated to understand. So it's related to the Galois connection. So I will just give the idea of what is a Galois connection and explain what is the link with interval method. So a Galois connection is two monotonic functions. So monotonic here with respect to some order relation, but for us, it will be the inclusion. Okay, so I will explain later, but I give first the what is the definition of a Galois connection in general. So you have two monodic functions, one which can alpha and one which is gamma. So A is the concrete, for us will be the concrete set, so the set of all sets of Rn, and B will correspond to the set of all boxes. But here it is not like this. It is A and B can be just order sets. And what is important is to have this equivalence. And I will explain this equivalence at least in the context of boxes. So with boxes, alpha associate to, so you have two different sets, A and B, and A corresponds to the set of all subsets of Rn, and B corresponds to the set of all boxes. So on the right, you only have boxes, and on the left, you have sets of Rn. So let me take X of this. In the abstract set, so on the set of boxes, it will correspond to a box. And here I also represented the initial set X, but it has normally, I should not represent it. So I have alpha of X is a box in this one. And I can, the gamma, associate to a box in this set. So what is important here is if I have this definition, it means that if Y contains alpha of X, so like this, then it is equivalent to say that this set X is included in the corresponding box. So here it's not the case, but what is important is to see this equivalence. So if you have this equivalence, it means that there exists a smallest box which encloses the set. But it's not sufficient. You have plenty of properties here, and probably the better way to see what is important in these properties is to consider other type of sets, as it is classically done in control. So a possibility, for instance, is to see if it is the case with sphere. So I have my set X, and here there exists a smallest sphere which contains X. So it is unique, and it is related to the diameter of X, so it is unique. Here in the abstract set, I have the set of a sphere here, and this one I can associate alpha of X here. Okay. And I can see that I have only the implication here. Indeed, if this, I can see that I have a sphere which, so I take a situation where I have X, such as this one, which is included in gamma of Y, which corresponds to this sphere, and which also corresponds to the sphere Y. It's some kind of identity. And I do not have alpha of X, so this sphere, which is included in Y. So I do not have a Galois connection here, and it means that I may have some properties. So for instance, the intersection of two spheres is not a sphere, and it is it will be difficult to use a forward-backward algorithm and to have all properties that we usually need. Okay. Another possibility is to see if I want to deal not with a sphere, but with oriented boxes. So if I take, for instance, a set, I can have the feeling that there exists, I want to use approximation using oriented boxes. But I can see that if I have a triangle, I have several, here in this situation, several smaller oriented boxes that contain this one. So in practice, it may be difficult to deal with oriented boxes, and it is why I want to exclude here loaner type algorithm, at least in a first step, because loaner algorithm use oriented boxes. So I will have some problem. For instance, the intersection between oriented boxes is not an oriented boxes, so I have to approximate it, but the approximation is not unique. So I may have also some algorithms that are not isotonic, and so on. So that's what we want to avoid here. Okay, but I still remain convinced that for sequences, as what we deal in this presentation, loaner type algorithms are probably the best. Okay, but it has this problem. So now I will explain why I want to consider boxes only, even if I deal with sequences. So I will introduce now the notion of directed contractors. So what is a directed contractors? I give first the definition. I have a constraint or a function f, or a constraint which has this form, y equal f of x. And I have what is a directed contractor? It is a pair of two operators, so the forward and the backward. And I want to have the two following properties. I mean, the forward contractor enclose f of x. Okay. So, and also I want the backward contractor like this. So I will explain just after with a picture, just so it will be more natural, this definition. And I also want the some monotony, which are given here. I mean, if A and B are included in X and Y, it will be the same after the contraction. But let me give you just an illustration with a picture. So here I have a function, y equal f of x, so f is a function, and I have x and y. So for the forward contractor, I take x and compute all the images by f, and I obtain a forward, which may not intersect y. So in this situation, you can see that maybe the term contractor is not the best one, but the contractor is mainly related to x. So after the backward, I will perform, I will make the intersection given here. So it means that I will take all pre-images that are consistent with both y and c, and I will obtain this contractor. So I will this box, and I can see that this backward depends on x and y, but the forward depends only on x. And probably to understand this, it is probably, so I will give some example just after. Okay. So let me come back to my initial point.
Luc, may I briefly interrupt you? Yes. Do you restrict yourself in this case to the identical dimensions of x and y, or may the dimensions be different?
No, general. No. It can be for any type of dimensions, of course. Any type of dimension. Okay. Okay, so let me continue. I have my set inversion problem like this, and I want to compute the set of x with the inside and the outside, but up to now, I do not just the contraction. So I have my chain like this, and I want to compute this. So I represent the chain like this. And here, what is important with the directed contractor is that we can compose them in this way, which was not possible with classical contractors. Okay, so if I do this, we can understand that we will perform a contraction, this one and this one and this one, the intersection, and after I will come backward. And this row here and here means that I have to memorize some information during the forward propagation step to be used in the backward propagation step. So it is a representation of the forward-backward algorithm, which has been explained before. Okay, so if I want to give a definition of the composition, I can give this definition, and for 3, it will correspond to this, but we can see, if I have here the composition of 3, but in fact, this composition corresponds to the forward-backward algorithm, but the way to put the composition in this form will allow us to probably have an algebraic way to write the contractors I want. So instead of an algorithm, I just put an algebraic expression, which is sometimes comfortable. Okay, so I will not enter too much here. And I will try to give an example of a directed contractor, which is classical for probably all of you, and given here.
We have a short question in the chat from Natalie. Natalie, may you, do you want to ask?
Yes, in the previous slide, apparently there is a C2 with an arrow on towards the left, which is missing.
Oh, okay, so on the previous slide, this one, yes?
Not this one, so the next one.
Next one, yes?
Yes, here. In the big formula on the lower right part of the slide.
Yes.
C1 and C3 with the left arrow.
Yes, this one?
Yes,
No,
and there is no C2.
One. Yes, yes.
There should be a C2 between C3 and C1. This the C3 you are showing.
I have some problem. Sorry. Okay. Yes. I have.
If you don't,
Oui.
your pointer was on C3, and
yes.
I think there should be a C2 on the left of it. No, this is.
That's what you mean. Probably it's wrong. Yes, yes. I see what you mean. Yes, probably you're right. Yes,
Okay.
Yes. I have to rewrite this. You're totally right.
Thank you.
Okay, thank you, Natalie. Okay, thank you. Okay, so let me give you now minimal an example. So you have a function here, which is a sum, and I can see that the forward corresponds to this one, and it does not depend on y, and for the backward, it depends on x and y. So it is quite well known, this, but just it was an illustration. And this one is minimal, so it is known to be minimal. And classically, we say because x1 is x1 occurs only once, and the same for x2. Okay. So now let me continue. What is a function for which we have minimal directed contractor is said to be contractible. So for instance, this one, this function f, the sum, is contractible. So it is probably a term, I don't know if there is another term for this, but I will give you some an example which corresponds to a linear equality. So assume that I have y equal a of x. So for instance, I will assume that a is invertible, so it is square and invertible, but it is not needed in general. And but just to write the expression. So if I have this, the forward is given by this, and the backward is given by this. And due to A is not an interval, it is known exactly. And in this case, we can see that f of given by this product is contractible. Okay, because I have the minimal contractor. I have many minimal contractor, but this one will be used later. That is why I give it here. So if you have any question, don't. So now I will come back to the decomposition and show how any function can be decomposed into a contractible function. So what is a contractible decomposition? It is a composition like this, such that each fi is contractible. So we have a minimal directed contractor for them. And not all functions can be expressed like this. And an example is a Fresnel integral that has no closed form with classical function. And this one cannot be decomposed in this way. But most of the functions we use that can be described by an algorithm have a contractible decomposition. So I will after explain how this can be decomposed automatically. But let me give you an example of contractible decomposition. I take this function. So I have the sum, square, and so on, but I can imagine that I have a more complex expression. So I have several types of decomposition. The one I call scalar, like this, because I do not deal with vectors. Each arrow corresponds to one real number, if you want. And I have what we call usually a DAG, directed acyclic graph. And for this, I can perform a forward and a backward. And this algorithm is named as HC4 revise algorithm when we deal with intervals. Okay. But it is much more efficient to use vector decomposition, still contractible with contractible decomposition, where I have the matrix and the norm. And if I do this, I am more efficient in terms of contraction. So let me give you a very simple example. I take this expression, I perform a forward-backward using the scalar decomposition, so HC4 revise. And if I use a vector decomposition, I obtain directly the red box without any bisection. So it's just an illustration to show that the vector decomposition is much more contractant in general. Okay. Okay. So now I will explain you how this can be performed automatically, the contractible decomposition. So I take here an expression like this with some exponential and so on. And I want to have an algorithm for the contractible decomposition for this. So usually what we do, we represent the expression by a DAG, directed acyclic graph, like this. And this DAG corresponds to the expression. So what we do, we start with what we could call here the leaf, so x1 and x2, and we will go forward. So forward and cut, and we explain why forward and cut. So I go forward like this, and I go forward, still I'm linear. So 3, 2, plus, minus, everything are linear operator. And I go forward, I go up until I'm stopped by nonlinear functions such as sine and multiply. And this corresponds to one matrix, which is given by this, and one matrix corresponds to a contractible function. So a matrix is also a linear operator, but it's also a function, but it is also contractible. So, so it is my first step, and I'm stopped here. So I cut here, and I continue. So I have two parallel nonlinear functions, sine and multiply, and for each of them, I have an optimal directed oriented contractor. Okay, sine and directed contractor. Sorry. And for this, I have the minimal one, so it is a contractible function, this one, with 3 inputs and 2 outputs, because it is a multiplication. Oh, okay, so 1, 2, and 3, and 2, 1, 2 output. Okay, and I continue, but here I'm stopped by a nonlinear function, and the one here corresponds to the identity. I continue, this one is linear, so it is correspond to this matrix. And in fact, this forward and cut algorithm provides me this sequence. So as to continue with the question of Andreas, I can see that this decomposition is as not always the same input and the same output. Okay, so once I have this, I consider here a sequence of function, and the algorithm I want to the forward-backward algorithm with this sequence is given by a classical, or this algorithm can be seen as a classical, which is almost, in case of a scalar decomposition, corresponds to the HC4 revised algorithm. Okay, so let me continue on this, and I will discuss about the boundary approach that I want to develop here. Okay. So I consider a continuous function f, and the continuity is important to deal with the boundary. And I assume that it is defined everywhere. It is important to verify this, so I have no square root, for instance. And in this case, it is known that the boundary of x is included in the inverse by f of the boundary of y. So I will give you an illustration here. I have here R, for instance, a function, and here R2. And the set I want to inverse, say, is a disk, but the closed disk. So I assume that the boundary, just for the illustration, the boundary is inside Y. So the boundary of Y is included in Y. And here I have represented the image by f of R by this. So here it is defined, here it is not defined, and defined, and here it's not defined. So we can see that the inverse of the disk corresponds to 1. So here it's 1 of 1, okay? For 6 and 7, 8. Okay, so it is the pre-image of Y. What about the domain of F? It is a set of all points that have an image, and we can see that 2, 3, this one, and 2, 3, and also 6, 7 have no image. And I can see here that the boundary of X, like this, is not included in the inverse of the boundary of Y due to the fact that I have some points that have no images. Probably this picture illustrates the problem we may find when we deal with the boundaries. Okay. Okay, so let me continue. If I want to deal with boundaries, what I propose is the forward sequence as we had previously. So X is a set of all points at time K that are consistent with the initial set. Here we make the intersection only with the boundary, okay? And after we have the backward sequence, but we can see that A is only consistent with the boundary. Okay. So if we do this, let me show you a picture of what we have at time K. Here it is all points that are consistent, so in red, with the future, so with Y in the future. Here in blue, we have the points that are consistent with the initial condition, with the past. Okay. And what we want to enclose at each time K is the intersection between the red and the blue. But it is much more accurate, much more efficient, if you want, to enclose the intersection between the boundary here in red and the set X of K. So it is the one we want to enclose, and we enclose in a box which is here named A of K. So it is it expresses what I want to enclose. Okay. Now it will be important to remember and to propagate backward the colors of each face of the green box. Okay. So let me show you the sequence. I start with a blue box, I compute F1 and so on, and at the end, I obtain here a blue box in the Y space. Here, this one, I can see that it is red, and this one will be outside. So I will memorize the colors, and I will now explain how we propagate backward. At each time, the box A of K encloses the intersection between of the set of all points that will send on the boundary of Y. Okay. So to explain how the backward propagation of the colors can be done, I will introduce the cardinal direction. So a cardinal direction is a number, so here 2 and minus. So it will give you, it means that if I have a box, I take the second interval, and minus tell me that I take the 3, because if I put my plus, it would be the 4. Okay. So each cardinal direction corresponds to a face. So the face, for instance, associated to lambda equal 2 minus, so x lambda equal to 3, the bound corresponding to lambda, and the associated face is this one, okay, 3, 3. And the set, I will define h of lambda, which corresponds to all points that to the half space corresponding to 3. So it is a set of all points that can see 3 from the outside. Okay. So let me also introduce a notion before explaining the backward propagation. If here I have two boxes, A and X, and I have also a cardinal direction. So here, since I am in 2 dimensions, I have 4 cardinal directions. So I can say north, west, south, east. Okay. So I can define here the box corresponding to this as the set of all points in X that intersect h lambda of A. So I can see that here I have 1, 2, 3, and 4 wind boxes. In this situation, I have 2 wind boxes, here 1 wind boxes, and here 2 wind boxes. So it can be connected or not. Oh, it's okay. So now, how to propagate backward the colors? So I can say that I have a box X. A corresponds to the contraction with respect to the boundary. And to each bound, I associate the color, which can be blue, red, or yellow, or it means outside, inside, or I don't know. Such that, for instance, when I'm 1, it means that the boundary is sent inside Y. When it is 0, this boundary, this face, is sent outside Y. So we need to have this property. So here, just to explain how it is done, I have here my box at time k-1. I have here my faces. I take 1 point just for an illustration, but you will not compute this point. If it is sent here in the part of the box which is known with a wind box, which is corresponds to the red, then this one will irritate from the color of this one. Okay, so probably the best now is to give an example with a sum only. I have my function f, which is given by the sum. The forward step does not deal with any colors, but the backward step is the same as we use classically, but here without any computation, but only with comparison of the bounds, we are able to irritate from Y to irritate in the A box of the colors, so like this. So it's not so easy to understand. It's better to, I will not enter in the details, but this can be shown properly, and the idea is the same as we have expressed before. So I would like to give you probably some codes just to illustrate what we have here. A sum. We have here, so it is classical, the forward propagation of the sum. Here is the backward propagation of the sum. And we can see that it is the same as we have usually, but just here some comparison, just to give the colors to X and Y. The same can be done for the square, and also for all classical functions. So let me come back to my presentation here. Okay, for the square, it will be very similar. The forward step is the same. Here, I compute the backward step of the square as we do usually, and we perform some comparison without any more computation. We can see here that I have a square, but I don't need to compute it because it has been computed already in the forward step. So only comparison allow me to backward propagate the colors. Okay, so now let me present some test cases. I have my set inversion problem, such as given by this expression. I have here a contractible decomposition of this function. So the sum plus s squared. So it is the way I write the contractible decomposition. And if I draw the set, I obtain the inside and the outside. But so I was able to backward propagate the colors, just focusing on the boundary only. And I can see that I have more information than usually, since I have some orange boxes and also some yellow boxes. In the orange, it means that I have proved that one face is I have different color. One is magenta, the other is blue. So this can be used and can be important when we deal with quantifier algorithm, when we need projections. Okay. So now let me also give you another example. I have here a robot, which is at point x1, x2. And I have some station, so 1, 2, and 3. And when we deal with a pseudo-range multilateration, it means that we do not measure the distance between the station and x1, x2 because of the propagation time and the clock are not synchronized. But usually the emitters, the station, emit the same sound or the same wave at the same time because they have good clocks, atomic clocks, for instance, and they are all synchronized. So they send a sound, for instance, or a wave, and we received it. And with a timer, we are able to see the delay between the reception of the signal from this station and this station. So in fact, what we are able to measure is a difference of distances between the station, so of distances to the robot. It is what we call the pseudo distances. So here the pseudo distances are 8 and 4. Okay. So in this example, f corresponds to my distances, my pseudo distance, more or less a given value. So here it is quite accurate. And my function f is this one. I propose the following contractible decomposition that has been obtained by the forward and cut procedures. And we can see that if we use a classical HC4 algorithm, we obtain much more boxes than when we use the forward-backward procedure we propose here. So we have less boxes, well, 3 times less, but also since we just compute on the boundary, we do not need to perform twice the computation from the inside and from the outside. So we have we can win some computation on this. So what about the perspective? The perspective is, of course, to use a loaner type algorithm and to extend the definition by assuming that the contractor is not necessarily monotonic. So of course, we may we may lose some properties, but it allows us to take into account to have better contractors, and by assuming that maybe non-monotonic. Of course, we would like to use oriented boxes, such as in the loaner type algorithm, but also ellipsoids or other type of wrappers for my sets. Okay, so thank you for attention. And if you have any question, please ask.
So many thanks, Luc, for your presentation. Does anyone want to start with questions? Okay, maybe let me start. In your implementation so far, did you extract this decomposition more or less manually? Or do you have some proposition to do this in an algorithmic manner?
Okay. So about you probably...
For example, on the previous slide.
You mean, excuse me, I will come back here. It is this algorithm. Yep. So at the moment, of course, I have done it manually. But what we need to do is just, it could be done automatically, but for this, we need to build a parser to build the abstract syntax tree associated to this expression. Okay, like this.
Yes, I assume that's a similar approach like you would do, for example, in procedures for algorithmic differentiation.
Yes, similar. Yes, we always need to build the abstract syntax tree or the DAG associated to the expression. But once I have this under the form of DAG, it's quite easy, but I've not done it. I do everything manually. I've done it manually here. But this can be done, of course, automatically, but it has not been done yet.
I guess I had the same question, yes, because according to the fact that you have linear function or not, of course, you use vector or not. I guess that was the question. And the two examples you provide at the end, the first one is linear and the second one is with non-linear function. If I am right.
No, not the first one was not linear. It was this one.
Yes, it's not linear at all. No. Also, yes, because you have a square function in the second one, but here you have also square function.
Yes.
Okay. So you have this type of decomposition in both cases, in both examples.
Yes.
But manually.
Yes.
Okay.
Andreas, may I ask a question?
Yes, please, Bernd.
Yeah, Luc, first of all, thank you very much for this very nice presentation. And I have a question. Can your approach be used to design also observers for discrete time nonlinear systems? Because when you have in a natural way this concatenation of the right-hand sides of the state space equations, and what you call F1 circle F2, F3, and so on. In that case, it's all the same F. And when you do what you have done here, this is a kind of observer for such systems.
Exactly. Yes. I think the way. Let me come back here. Probably when I do this, I think the way of thinking is totally related to control and to observer theory.
Right.
The forward and backward is a Kalman smoother act exactly in this way. So, of course, when I say that K is time, it's directly the language of observers. But you can see that in practice, for many people that solve equation, let me, for instance, this one, there is no time. But me, I prefer to transform it into a sequence like this, and to have the iteration is replaced by time K, and I exactly perform an observer. But even in Kalman observer, for instance, the block like this may depend on time. The matrices may depend on time. But even for the Kalman filter, the dimension can change.
Yeah.
But I don't think I would call it an observer. It's more a smoother, because it's not necessarily causal. Yeah. I want a forward and a backward. So it's more what we could call a smoother in practice. Yeah.
Okay, yeah, you also give up causality in that case.
Yes, I don't want the causality. I want to inverse the problem. So I want, I need the causal. I need to perform forward and also a backward to make X and Y both consistent each other.
Yeah. Thank you very much.
Thank you.
Okay, we have a further question from Tarek.
Yes, thank you, Luc, for this very nice presentation. I have the same question about estimation. So we can use these techniques for estimation. What about the computation complexity of such techniques for estimation, for example? And the second part of my question is how to ensure the stability of the estimator with this technique? And what about the robustness with respect to uncertainties? Is it possible to include, for example, some optimization criteria to have some performance like H infinity performance or L infinity?
Okay, so you have several questions. So your first question was related to
the computation complexity for the first.
So the computation complexity of when we perform bisection, it can be so when we want to be accurate, we need bisection, and in this case, it is exponential with respect to the dimension of the state space. But in practice, when we want to deal with a large dimensional problem, let's say the dimension of the state is 100, for instance, we do not want to use bisection. And in this case, we need redundancy. We need to have many measurements so that the contraction algorithm could work. And in this case, I would say that the complexity of just one forward and backward could be linear with respect to the number of measurements we take, and also so it will and also linear with respect to the length of the expression of the fk, if you want. Mm-hmm. So I have to do the product to have the complexity of the whole procedure. So I think it's very, very fast. We can use this type of characterism in robotic for SLAM problem, where we have many unknowns. And in this case, I would say that it is even for large dimensional problem, it goes very fast. Now, concerning the stability, so your second question, it is stability. So in fact, when we deal with this kind of estimation problem, it's like dealing with the stability of a Kalman filter. We have to, it's not a dynamical system. Here I just have a set inversion problem. So I do not have, I would say that I have no, I consider a sequence which is finite. So I have a composition and function, but for instance, here I have 1, 2, 3, 4 blocks, and that's all. I do not an infinite number of blocks in the problem I deal here. So I think there is no meaning, there is no link directly to the stability in the Lyapunov sense, since I have not a sequence that goes up to infinity, but just an inversion with a finite number of steps. But of course, if I want to deal sequentially with the problem, maybe I could observe some differences when I want to deal with in an observer that consider measurements that arrive with time. But it is not the case here. Everything is static. I have a number of measurements that are fixed here. So I do not deal at all with the stability, and there is no results here related to the stability. Now probably you had a last question. It was related to H infinity, yes?
For example, is it possible to add some optimization steps with this estimate as a function?
It should be possible, but the problem that is solved here is a set inversion problem. So if I want to formalize a problem as a constraint, for instance, a set inversion problem, and I have a set which is defined by inequalities, and now I want to optimize a criterion, let's say a non-convex criterion, then I will need contractors for the constraints, constructors for the criterion. And the criterion may be complex, may be decomposed into a sequence and function. And to construct these contractors for the criterion, but also for the constraints, the method I have shown here can be used as a tool to provide these efficient contractors. But everything has to be plugged inside an optimization procedure that has been thought with respect to contractor-based approaches.
Okay, thank you, Rick.
Okay, thank you.
Okay, do we have any further questions?
I have one, but it's really an open question. If I understand well, you put, Luc, you put color tag according to the fact that the face of the box is outside or inside. So you have 3 colors.
Yes, yes.
Perhaps outside, inside.
Yes.
And do you believe it could be interesting to have a continuous color tag, so more than 3, and not only to have an information about outside, inside, but also about the fact you contract a lot or not?
No. I think
from an optimization point of view, okay. Do you believe this kind of information could be useful? Because I understand that with the color, you avoid an extra computation during the backward phase. But if you have this additional information, are you able to use it?
Yes. What I want to say, I will answer. See, is at the beginning, I want to solve a set inversion problem. So a set inversion problem, we have different type of values when we deal with boxes. We are inside, outside, or uncertain. And what calls Peter Collins is in his talk said about the Kleinian values. Yes, you have only 3 values. Now, maybe why it is an uncertain set and you want to represent by several nested sets, like it is classically done when we deal with fuzzy approaches. Then in this case, it would be quite interesting not to compute for each YE the values, but to do it only once as it is done here. And in this case, it is important, we'll have more than 3 colors, and it will be important to retropropagate these colors as I have done here. But in the pure set inversion problem, there is only a Kleinian value, so 3 values, 1, 0, and maybe.
Okay, thank you for the answer. Yes.
Thank you.
Excuse me, may I ask a question?
Yes.
And a question from China.
Yes.
Thank you for your good presentation, and your presentation is very interesting. But to be honest, it is little complicated to me. It seems a mathematical problem. So here I'm majorly concerned with the application of the theory. can you make some more comments on the application of the theory to Angiolini? For example, can the theory be connected to the control theory? How can it be used applied to the control theory?
So I am not sure I have understood your question, but you mean if there is some
consider with the application of the theory.
Of the theory, yes.
Yeah.
Yes. So here in this talk, I did not probably discuss too much about the application, but when we deal with a classical set inversion problem. So set inversion problem is one problem which is it is a view of what it's an inverse problem. So it's an inverse problem are used for estimation or for localization, or a lot of problems can be formalized into inverse problems. So of course here I wanted to explain with interval methods how we solve inverse problems with a set membership approach. But what it's not, I agree that I do not present a convincing application. It was not the goal of this talk. It was mainly to make a theoretical talk to explain how we can avoid computation in set inversion methods. So avoiding, so the main application could be said to avoid too much computation and to go faster. But I agree that it was not a convincing, I did not present here a convincing application of set inversion method.
Yes, maybe let me add a further comment in this position. As you just said, look, you want to reduce the number of computational steps that are necessary in order to evaluate this inversion problem. And I think we already had in this discussion several practical applications. I think the first one was given by Bernd when he talked about discrete time state estimation. The second would be identifying parameters, for example. If you have uncertain outputs of a dynamic system and you want to solve again an inverse problem, you want to reconstruct suitable sets of system parameters. And I think also in the frame of simulating dynamic systems with bounded uncertainty in parameters, this can have a wide range of applications. For example, think of you making use of some Lohner type algorithm for integration, or you're using something like V-node LP, you're using CLPD for integration. And usually after some time span, your interval bounds may blow up. And if you want to tighten those bounds, you could use, for example, in a mechanical system, information about conservation of energy, in a fluidic system, information about conservation of mass or volume flow rules, in order to rule out some parts of the computed state enclosures that do not make physical sense. And I think such things concerning this question that we just had, I think there are plenty of applications in real life engineering scenarios ranging from state estimation, identification till simulation.
Yep.
Okay, thank you.
Thank you.
Okay, any further questions?
Hi, Luke, I have a question.
Yes, please go ahead.
What's the consequence if there are some outliers?
Okay, so if I have some outliers, I can transform the fact that I have outliers into a set inversion problem. So what you usually do, so I will try to take again, if I succeed to do it, no, yeah, okay. I don't know why it's maybe so compatible. So usually
Your cursor is showing zooming, not writing, not the pen.
You do not see what I write. Yes? No?
Now it's working.
It's working.
Yeah, it works. It works.
Oh, okay. So usually when I have, for instance, measurements, so y1 and y2, usually what we have a point which corresponds to a measure. Okay. And due to uncertainty, we have an interval for y1 and an interval for y2. And it corresponds to a box like this. When we have one outlier, we consider that so this one corresponds to the set Y we wanted to inverse. Like this. So when we have outliers, usually we transform like this. When we allow, and we say that instead of being in this box, we may be also here or here. We just transform Y so that we can relax some of the data, interval data. And in this way, we still have a set inversion problem, but the new Y corresponds to the green one. And the corresponding algorithm performed in the X space. So in the X space, this one will correspond to the set of all X consistent with Y1. This one, the set of all corresponding to X2, to the second one. And here, the set of all X corresponding to the third data, and so on. And when we want to perform this kind of relaxation, we still have a set inversion problem, but the set we compute is indeed what we call the relaxed intersection of sets that are consistent with the ith data. So I would just say in few words that dealing with outlier in a set inversion problem leads to a set inversion problem, and the corresponding contractor and the related notion corresponds to what we classically call the relaxed intersection. But it's difficult to explain in few words like here to do exactly what is done, but I try to explain here with few pictures.
Okay, so your algorithm will not stop when there are some outliers.
I think it will solve what you ask it to solve. Of course, you have to formalize your problem into a set inversion problem to apply the algorithm I propose here. But that's all I can say. It's not magic. We have to write your equation and your outlier into a set inversion problem, and it is possible to do it. You have to formalize in that way in order to apply the algorithm I have proposed here.
Okay, so you have to change the question, change the equation?
No, you don't have to change the equation. You mainly have to change the set you want to inverse. As I have said, instead of inversing the blue set like this, if you have some outliers, you inverse another set which corresponds to some relaxation, where you say that you just do not want to be consistent with all measurements, but you want to be consistent with all measurements except few of them. And it allows you to be robust with respect to some outliers.
What I meant is that what's the consequence if your algorithm does not know there is an outlier, but there is an outlier?
Okay. In this case, if you apply the method and you want to compute the set of all X that are consistent with all data, very quickly you will obtain that X equal empty set. It means that there is no solution. And indeed, there is no solution. So in this case, if you know that, for instance, it corresponds to the localization of a robot and you know that your robot exists, it means that you have a proof that there is some outliers.
Okay.
Okay. In this case, you can relax few interval data And using the concept of relaxed intersection, you are able to compute the set of all x that are consistent with all data except few of them.
Okay, thank you. Thank you.
Thank you.
Any further questions? Yes, Stefan, please switch on your microphone.
Yes, just a last quick question. The process you explained seems to be quite an automatic one. Do you believe or do you like to propose to incorporate these algorithms, CVA color-based algorithm into IBEX?
So IBEX, it could be done. It could be done. So I have not think yet about this because IBEX is used for this. We can use IBEX to, but now indeed, if we want to backward propagate it for a set inversion problem, probably we have to change some. We have to add some flags. Or some colors inside the core of IBEX. So it can be done, but it's not sure that it's a good idea because we change the core of IBEX, and at the moment IBEX has, which is made for contractors. For those who do not know IBEX, it's an efficient way. You have efficient contractors inside. So if you start to change the core, maybe you will incorporate some bugs. So we have to think about it. Okay, and there is many people in IBEX, and we have to discuss and to see if it is very interesting to do this.
That was the meaning of my question. If it is so easy to plug this kind of CVA algorithm into IBEX.
As soon as you change the core.
In a general manner.
Yeah, if you change the core, you may incorporate some bugs. Always the main problem. Okay.
Is there anyone else who wants to ask a question? So if not, thank you again, Luc, for your presentation and for your patience to answer all the questions at the end.
Thank you. Thank you to all of you.
Thank you for the presentation. Yes, interesting. I will think more about. Yes,
thank you.
Thank you, Luc.
Thank you.
Yes, thanks to all of the audience also for participating so briefly before Christmas. And I think I'll take the opportunity to wish every one of you a nice Christmas holidays, and hopefully you come well into the next year, and see you soon in the middle of January for the next presentation. The next presentation will then be on the 15th of January. Okay, have a nice Friday and nice weekend, nice Christmas holidays. See you soon.
Thank you.
See you soon. Thank you for the invitation. Bye.
Thank you. Bye-bye.